ECA students, this week we are looking at solutions. This week you can expect to have 3 assignments. Together they are worth 50 points. You have a quiz based on this slideshow, a lab with analysis questions, and a reading and response. And the next 2 weeks after this will look the same. In this video, let's go over part 1, vocabulary and concepts. Alright, so homogeneous or heterogeneous mixtures. Mixtures can be homogeneous or heterogeneous. If a mixture has the same composition throughout, it is called homogeneous, meaning same. You can't see the separate components in the mixture. Think of coffee. Coffee has cream, sugar, and water, and coffee beans, but they're all thoroughly mixed together. In contrast, you could think of something like salad dressing, where you can clearly see the separate ingredients, like the vinegar and the oil. This is because it is a heterogeneous mixture, which consists of visibly different substances. When we talk about solutions, we need to refer to solutions as being homogeneous. But they have 2 or more substances, which we're going to call solvents and solutes. So let's define those words. The solvent is the thing that there's a larger amount of. For our coffee example, that would be the water. The water dissolves the thing that there's a smaller amount of, say the coffee beans or the sugar. This would be called the solute. These words are easy to get mixed up. My only trick for you would be to note that solvent is a bigger word than solute because it has 1 more letter. Alright, this chart is very handy because it's going to be useful in your quiz. Solutions don't have to be just liquids mixed with liquids. They can be a mixture of different things in different phases. This table provides some great examples that might be handy. So let's look at the example of salt and water in bold there. In a salt water solution, the solvent would be the liquid water and the solute would be the solid salt. The salt is completely dissolved in the water, creating a homogeneous solution. You can't see the separate ingredients. Alright, we have 2 new vocab words, which are miscible and immiscible. So when we look at liquids, I want you to think all the way back to intermolecular forces, where we had polar and nonpolar molecules. Polar molecules were attracted to each other. 2 polar liquids would be miscible because they dissolve one another and become a solution. Immiscible liquids would be trying to combine oil and water. Liquids that are not attracted to each other because one is a nonpolar molecule and the other is a polar molecule. They, in fact, repel each other, as you can see in this picture. So the miscible solution of the 2 substances that have thoroughly mixed together, you can't see the difference between them with your naked eye. You would have to look at them on the molecular level, like in the picture there. If you take a look at the immiscible liquid, you can clearly see the lines where they are separated because they don't like each other. In chemistry, there's a phrase that says, like dissolves like. And this means that molecules that have similar characteristics, say they're both polar, have the ability to dissolve each other. So let me go on a soapbox about soap. Ha ha ha. All right, so if you look at soap, this long molecule here, it has a polar side and a non-polar side. This is pretty handy because about what we just said. Like dissolves like. But if you have both a polar and a non-polar, then you can dissolve both polar and non-polar molecules. So the polar head has the ability to dissolve water, which is handy, and the non-polar tail has the ability to dissolve nonpolar molecules such as fats or lipids. Lipid is just a fancy word for fat. This is very important to know because our coronavirus that's going on has something called a membrane envelope that's made out of lipids. And so when you have the lipid envelope that protects the DNA that would infect us, the soap can dissolve and break apart that envelope. And that's why it's so important to use soap during this time. All right, enough about soap, let's continue. The next vocab word is saturation. You've probably heard this word before. And you may think that's when a solution is saturated, that means the solute is no longer able to dissolve. I thought the same thing, but guess what? That's not true. So let's think about our example of iced tea. When you put too much sugar in iced tea, you might think it just sits at the bottom of the glass of tea. What actually is happening is the solute is in a state of equilibrium, meaning bits of it are going back into the state where they were before, which is the solid sugar, and other bits are dissolving. Saturation is actually affected by temperature. Back to our iced tea example. When you have iced tea, you can't put in sugar and expect it to dissolve very well. But when you have hot tea and you add sugar to it, it will dissolve much quicker. Then you can ice it and make sweet tea. That leads us to our next term, which is solubility. Solubility is the rate at which it takes for a solute to be dissolved in a solution. And this rate is very much affected by temperatures. Let's take a look. There are things called solubility curves that show the change in solubility at different temperatures. Here in red, you can see sodium nitrate has a very linear positive rate of increased amount dissolved as the temperature goes up. This trend can be seen when solids are dissolved in liquids. So all of these things are salts, and most of them have an upward either curve or linear rate at which they are dissolved depending on temperature. If we look at salts, they have the opposite reaction to temperature increase. So as the temperature goes up, the amount of gas that can be dissolved in water is less. You can see this in soda. When you leave it in the fridge, it has a crisp, bubbly flavor. Compared to when you leave it outside on a hot day, the soda has gone flat because it has less CO2 dissolved in it. All right, so what affects solubility? Oops. We know that temperature, we just talked about, affects the solubility rate. We know that the state of the matter, whether it's a gas, solid, or liquid, affects this solubility. And we know that the like dissolves like concept, if the molecules are attracted to each other or similar in nature, being polar or nonpolar, will affect the solubility rate. Here's the thing though. Dissolving solvents and solutes does not make a chemical reaction. When a solution is made, it's called dissolution. A dissolution is a physical change because you can make the solute go back to its original form by dissolving the solvent. Think of salt water. We can evaporate the water and we will be left with table salt. That was previously completely ionized and mixed with the water. An example of a reaction would be where a precipitate forms as a new product appears after the mixture has evaporated in the liquid, such as in the picture here. Completely new product. All right. And that's the end of this video. Next video will have part 2 vocabulary.